Welcome, my friends. I'm so excited because in this video we get to talk about the Poisson distribution. So let's go ahead and get started. In previous videos, we've talked about the binomial, geometric, and hypergeometric distributions, which were all based on 4 core conditions or modifications of those conditions. The Poisson distribution is a little bit different. This is a distribution which can be used when the mean number of occurrences of an event is known within a certain time period, area, or some other frame of reference, and each occurrence of the event must be independent. Let's look at some examples. The most common examples relate to time. Let's say that customers enter a travel agency at a mean rate of 3 per hour. We know the mean number of occurrences of an event within some certain frame of reference, in this case per hour. If we assume that the entrance of each customer into the travel agency is independent, then we could use a Poisson distribution to model this example. Let's look at a non-time example. This example says that a type of aluminum screen has an average of 1 flaw in a 100-foot roll. So once again, you can use the Poisson distribution whenever you know the mean number of occurrences of an event within some frame of reference and that each occurrence of the event is independent. So if we assume that each flaw that was found in this aluminum screen was independent of the previous, we could use a Poisson distribution to model this situation. Now, since the Poisson distribution comes from the mean number of occurrences of some event, we use a special symbol to represent the mean, and that symbol is the Greek letter lambda. This notation here says that our variable x follows a Poisson distribution with a mean of lambda. So we say that the mean mu of a Poisson distribution is equal to lambda, and the standard deviation turns out to be just the square root of lambda. Interestingly enough, this means that the variance, which is the square of the standard deviation, ends up being lambda as well. So this distribution has a mean and variance which are equal, which is kind of interesting. On the other hand, the Poisson CDF function is going to solve for the less than or equal to probability. For example, we could solve for the probability that x is less than or equal to 2, which would mean the probability that we have 2 or fewer occurrences of x within our frame of reference. Let's take a look at an example. The rough draft transcript for a speech contains 2 grammatical errors on average for every 150 words. Let's assume independence of the errors. Let's let our variable x represent the number of errors in a 150-word segment of this draft. Since we know the mean number of occurrences of some event within a frame of reference, in this case a grammatical error within a 150-word section, and we have independence of the errors, we can say that our variable follows a Poisson distribution with a mean lambda equals 2. Now, we know that on average, we will have 2 grammatical errors for every 150 words. But it could be the case that we have 3 errors, or maybe 1 error, or 0 errors. The Poisson distribution will find the probability that we have any number of errors within a 150-word segment. For example, we could answer the question, what is the probability that there are 3 errors in a 150-word segment? This question is asking for the probability that x is equal to 3. Once again, remember that on average, we would only expect to have 2 errors, but this question is asking what's the chance that we have more errors than average, specifically 3 errors. Remember that we can find the equal to probabilities by using the Poisson PDF function. Let's go to the calculator. On the calculator, you can press the second key and then the vars key, which the second option is for distribution. Scroll down, and you will eventually see an option called Poisson PDF. Press enter. You will be asked for 2 different things. First, we are asked for lambda, which is the mean, in this case 2. Then we are asked for the x value. We're trying to find the probability that x is equal to 3, so we will put in 3. Go ahead and paste, and then press enter, and you will get the answer of about 0.1804, or about 18.04%. On average, we would expect to only get 2 grammatical errors in a 150-word segment, but it's possible to get 3 errors, and there would be about an 18.04% chance of that happening. Let's look at another example. We are asked what the probability is that there are fewer than 5 errors in a 150-word segment. This is asking us for the probability that x is less than 5. Remember that we only have 2 functions in the TI-84 to calculate probabilities on the Poisson distribution. We have the PDF function, which calculates the equal to probabilities, and we have the CDF, which calculates the less than or equal to probabilities. we don't have a function that finds the less than probabilities, so we need to convert this to less than or equal to 4. Less than 5 is the same thing as less than or equal to 4. So we can use the CDF function on our calculator and plug in 4 to find the answer. Let's grab our calculator again. We can press the second key, then distribution, scroll down, and we will eventually see the option for Poisson CDF. Press enter over that option. We still have a lambda value of 2, but now we're going to put an x value of 4. Go ahead and paste, press enter, and you're going to get 0.9473. The probability that there are fewer than 5 errors in a 150-word segment is 94.73%. What about the probability that there are 2 or more grammatical errors in a 150-word segment? This problem is asking for the probability that x is greater than or equal to 2. But once again, we only have 2 functions in the calculator for Poisson probabilities, the PDF for equal to and CDF for less than or equal to. Therefore, we're going to have to use the complement rule to change this into a less than or equal to probability. The probability that x is greater than or equal to 2 is the same thing as 1 minus the probability that x is less than or equal to 1. The complement of greater than or equal to 2 is less than or equal to 1. Therefore, we can use 1 minus Poisson CDF with 1 plugged in. Let's go to the calculator. On the calculator, we can press 1 minus second distribution, scroll down to Poisson CDF, press enter, put in 2 for lambda and 1 for x, go ahead and paste, press enter, and you'll get the answer of 0.593, or it looks like 5940. The probability that there are 2 or more grammatical errors in a 150-word segment is about 59.4%. All right, let's try one more problem. What's the probability that the number of errors in a 150-word segment is equal to the variance? Well, remember that the standard deviation of the Poisson distribution is the square root of lambda. That means the variance must be just lambda itself. And we already said that lambda is equal to 2. So really, this is just asking for the probability that x is equal to 2, which you can find by using Poisson PDF. I'll let you check the answer yourself, but you should get about 0.2707. The probability that the number of errors in a 150-word segment is equal to the variance is about 27.07%. Let's look at one more example. On average, a clothing store gets 100 customers a day. Let's let x represent the number of customers the clothing store gets in a day. If we assume that the occurrence of each customer is independent, then we can say that our variable x follows a Poisson distribution with lambda equals 100. Let's say we are asked what the mean and standard deviation number of visits per day are. Well, the mean is just equal to lambda, which is equal to 100. The standard deviation is simply the square root of lambda, which is the square root of 100, or 10. What is the probability that at least 100 customers visit the store in a day? Well, that's just the probability that x is greater than or equal to 100. Once again, we don't have a function in the calculator to find greater than or equal to probabilities, so we must use the complement rule. The probability x is greater than or equal to 100 is the same thing as 1 minus the probability x is less than or equal to 99. We can find this answer by taking 1 and subtracting Poisson CDF with 99 plugged in. Let's go to our calculator to plug this in. We can grab our calculator and we can go to 1 minus second distribution, scroll down to Poisson CDF, put in 100 for lambda, and put in 99 for x, paste, and we will get an answer of 0.5133. There's about a 51.33% chance that at least 100 customers visit the store in a day. Now, sometimes in a Poisson distribution problem, the frame of reference might be changed in the middle of the problem. For example, consider this question. What is the probability that less than 750 customers visit in a week? Well, our initial problem said that we would expect to get 100 customers in a day, but this question is asking about the number of customers in a week. So we actually need to define a new distribution. We can let y represent the number of customers the clothing store has in a week. If we know that on average we get 100 customers in a day, then we know that we are going to get an average of 700 customers in a week. So we can say that y follows a Poisson distribution with a lambda value of 700. We are asked for the probability that y is less than 750, which is the same thing as the probability that y is less than or equal to 749. We make this change so that we can use the Poisson CDF function. If we use the CDF function, plugging in 749 for the x value and 700 for lambda, you will get about 0.9683. There's about a 96.83% chance that we have less than 750 customers in a week. Alright, here's a problem for you to try. A type of aluminum screen has an average of 3 flaws in a 100-foot section, and you're asked a number of questions about this. So pause the video and give it a shot, and I'll be back in just a minute to help you through some of the problems. Alright, hopefully you've given the problem a try. The first thing you probably should have done is define our variable x as the number of flaws in a 100-foot section. We know that x is going to follow a Poisson distribution with a lambda value of 3. We are asked for the probability that we have 3 flaws in a 100-foot section. Since we're asked for an equal to probability, we can use the Poisson PDF function with lambda equals 3 and x equals 3 as well. If you plug this into your calculator, you should get about 0.2240. The probability that we have 3 flaws in a 100-foot section is about 22.4%. Then we are asked about the standard deviation number of flaws in a 300-foot section. Well, now we no longer have a 100-foot section, we have a 300-foot section. So our new variable y is going to represent the number of flaws in a 300-foot section. Since this section is 3 times as large as the initial section, our lambda value will also be 3 times as large. We can say that y follows a Poisson distribution with a lambda value of 3 times 3, which is equal to 9. We are asked for the standard deviation, which is equal to the square root of lambda. In this case, lambda is 9, so the square root of 9 is equal to 3. The standard deviation number of flaws in a 300-foot section is equal to 3. Finally, we are asked for the probability that the number of flaws in a 300-foot section will be greater than the expected value. The expected value is just a fancy word for the mean, so they're really just asking for the probability that we will be greater than 9. So I'll let you try this one on your own. Alright, my friends, that's all I had to say about the Poisson distribution. So hopefully you found this video helpful, and I will see you in the next video.